Hello everyone, my name is Adrian Jensen with Applied CAX. Thank you for coming to another one of our technical seminars focused on Simcenter Femap and Nastran. Just to give you a little bit of introduction, we are a Siemens Digital Industries reseller. We focus on all things simulation, CAD, CAM, Teamcenter. We've got a whole crew, and we like to say we do this every day because when I'm not doing seminars like this, I'm building models. We have people designing parts. So we're really are doing this every day. And we kind of use those skills to help you guys out. So please reach out to us if you need anything. If you've done one of these seminars before, you know how it works. If you're new, there is a dashboard. There's a section for questions. You can chat or add in questions there. We'll try to get to them as we go if there's time, but this is a pretty packed seminar today. I'm going to be flying through all sorts of new features. So if we don't get to them during the seminar, we'll follow up via email, or you can reach out to us on the website. This is going to be recorded. It'll be available on appliedcx.com with plenty of other older seminars. We try to do these every quarter or so, and there is a huge library of stuff. So if you're ever having problems with modeling or trying something new, please check out the website. Another thing to mention is we have some training coming up this summer. We're going to do a live online training and seeing how things go, potentially some live in-person events up in the Northwest. So keep your eyes open for more news there. Okay, today I want to talk about what's new and more importantly, what's good in Femap V 2022. They do releases now every 6 months for Femap and Nastran, and with those comes new features. And rather than going just through every new feature that's out there, I've kind of curated the ones I liked, and I've actually gone back to 2021.1 and .2 and found maybe some of the new features from those as well that might have gone under the radar. So it's going to be sort of new features over the past year. I know it's easy to get set in the ways that you do modeling, and so I just want to expose some of these new things. I think a lot of them can be really useful, and it's worth taking a look here. Quick overview, we're going to do a bit in the user interface. They've updated the help files and the entity display. A lot of the updates we're going to be talking about today is focused around pre-processing, meshing, all different types of meshing, and the way that the geometry interfaces with each other using the Mesh Control Explorer. And then at the end, we've got a little bit of post-processing with JT files, and then also some new contour options that are designed to work with some of the new meshing options. So let's go ahead and dive in, and we'll start with the help files. So there's now a web-based help file situation here. Under preferences, you can set whether you want the new or the old help files, but they're trying to update and kind of modernize some of this. I know that searching through the previous help file browser was a bit of an art. So I think that maybe having this web-based help file can be a bit easier for finding things, a bit easier for navigating. But of course, you still have all of the old options there. And if you're old school like me and like to have some PDF files, in your install directory with Femap, under the help, there's the PDF files there. So you now have 3 different options for the way that you can access the help files. As for the user interface, this seemed kind of small, but I thought it was really pretty nice. The entity display toolbar. So this has been around forever, but they've added an update here where you can switch modes, and it allows you to switch back and forth modes, whether you want to display the entity or display labels on that entity. This was previously something that you had to go into the visibility dialog box to control, which is still useful and gives you a lot more granularity in the control. But the entity display toolbar is nice because you don't have to open it and close it. It's always there. Let's take a look at a model with all sorts of different entities, and I'll show you how this works. So I'm going to switch over to Femap here. I've got this model here, a service body for a truck with all sorts of different entities, geometry, mesh, and so on. And the entity display toolbar, here it is. I've made some slight modifications to it, adding some buttons here to show the full model, active group. And if you're unfamiliar with customizing toolbars, please check out our previous webinars. I believe maybe the very last webinar we did talked a lot about customizing the interface. So if you haven't done that before, we can teach you how to do that. But as far as the new setup for the entity display is you click this first button here. When you see the numbers, it's set to display titles for your entities. And when you see this symbol here, it's actually set to turn on and off entities. So we can turn off all of the geometry, all of the mesh, or individual entities of geometry and mesh. Now let's say we're just going to turn on our loads. We can switch over to labels and turn on and off our labels for those loads. Same goes for coordinate systems. This is nice because you kind of want to choose carefully what labels you turn on. This model's got about 150,000 elements. So if I'll zoom in here a bit before I turn on my labels for elements, because it can really flood the screen with all sorts of labels. So you kind of want to choose, maybe make a group of just the entities that you want to look at, but be careful with turning on labels because it's displaying a lot of information all at once. All right, like I said, a simple little tool, but really pretty useful. And it just makes navigating your model that much easier. All right, let's dive into the more advanced pre-processing. Now, there's been big updates to Femap with the Mesh Control Explorer, and this affects a lot of different aspects of building and meshing a model. In one of my previous seminars, the surface modeling, we introduced this, and we talked about how you can have different geometric entities communicate with each other, have consistent mesh sizing without all being added together. Previously, for surface modeling, we would be creating a bunch of mid-surfaces and then using non-manifold add to join them all together into one continuous sheet solid. That's no longer necessary. I'll be honest, I'm still getting used to this technique, so it's not, I'm not 100% converted to the new technique here, but it is really nice, and I've found, kind of surprised myself at certain times working through a simple model and realizing, oh, all my elements are lined up. I can skip some steps here. Now, this is controlled through the meshing toolbox with this option here. You don't have to use this. You can turn this off. You can also set tolerance, exactly what type of edges or solids to pair. So you could select just certain parts of your model, certain solids, certain types of edges, and that way you get to control how much of the model, how much of the geometry is automatically pairing things up together. And I put this in here more as a guide for you guys to download and use later on. This little guide was actually put together by the Femap team, and it shows you what each of these buttons does. Let's just go ahead and jump over to the software and you can see how it really works. But this will be a nice guide later on as you're exploring this tool with some of your own models. All right, I have a simple little model here. This is, if we take a look at the model info tree, this is just a bunch of individual surfaces. Each one of these surfaces is its own solid. They're not stitched or non-manifold added to each other. Each one of them is totally independent. Now, previously, we would want to stitch these together, use non-manifold add, because when we take a look at some of these surfaces, for example, this one on the side, it's not broken. The edge curves aren't broken where it meets up with its neighbors. So we wouldn't have a node right there to join up with the node along the top face. Same thing here, there's these these split points where the sides have it, but the top doesn't, and vice versa. With the Mesh Control Explorer, we don't have to worry about that as much. So let's just go through a standard workflow where we would set up our size on surface. Let's select all these surfaces, do something like a 0.1 mesh size. If we wanted, we could preview that mesh size with this mesh size location option under the view style menu. And right here, you already notice that these little white dots for the mesh sizing are aligned. If we go to actually mesh the surfaces, we'll select all. We can just use plot elements because we're not going to be running analysis. You can see that the mesh is aligned. Now this is a fairly fine mesh. We could have gotten lucky with this size here, but feel free to download these models later and test this out with different mesh sizes. It's going to stay continuous in terms of the sizing between the different parts, and that's because of the Mesh Control Explorer. So this tool is within the meshing toolbox, and it is right up here. Explore Mesh Control and Sizing Propagation. When we click this, it opens up a new pane within Femap. And here's all those different buttons that you saw in the presentation. And if you slowly scroll over these, it'll tell you what each of these is doing. So this tool is useful for other types of meshing as well, not just surface meshing, but we'll get into that into a minute here. So it's important to go slowly, hover over these, and the titles will give you a lot of information. So match surfaces, nothing there. We're not matching up different solid bodies. We're not using any special matched approaches. But this one here, show edges paired by mapping and proximity. Now, when I click on that, it gives me a list of curve ID numbers, and it also highlights those curves here. So this is showing me where curve 27, 14, and 6, which would be the curve along the top edge of the side, and the two curves along the side of the top of the box are all joined together, are all paired together. So these combinations make sure that you get continuous mesh sizing, even though I have totally separate bodies for each of these surfaces. And this can kind of be nice to keep your bodies, your geometric bodies separate, especially if you like to use the draw erase toolbar, because now I'm not going to erase the entire sheet solid because they're all independent sheet solids here. So it gives you a little bit more flexibility of control. One of the other things this is really useful for is with hex meshing. And that's where the show slave surfaces button comes into play here. We can not just pair up different edges to each other to match mesh size. We now have some place to document and to look at where different surfaces are paired together in a hex meshed solid. So let's use the same tool, but rather than plate meshing, we're going to go ahead and switch over to hex meshing. I'm going to start a new model. I'm going to import some geometry, and I have this sample geometry here. Now you can tell if you're experienced Femap users from the colors. This is already letting us know that this is a hex meshable part. If you ever want to reset the colors on any sort of entity in your model, under the modify menu, they give you the options for all that. So let's reset all of this back to a uniform color. Now I'm going to go to mesh, control, size on solid. We'll go with hex meshing, and I'll do something like 0.5. Now, when we set our sizing for hex mesh, this is where it changes the colors, letting us know this has always been the case. We can take a look at our mesh size, see how fine or coarse we want it. We also get messages in the window down here telling us which surfaces are linked together. And again, that's always been the case for Femap. None of that's new. And if you're not really familiar with hex meshing, we're going to have a dedicated hex meshing seminar coming up next. So we'll dive into some of the details that a bit more. But what is new is we now have the Mesh Control Explorer to see all of these paired faces together. These are actually showing these matched faces and showing that we kind of have somewhere to document and see where these are stored together. In terms of matched edges, that's not really necessary. That's more of a surface modeling type of thing here. Now, it's not really something we need to actively manage or do anything with. It's almost just documentation of what's been paired together at this point. But let's mesh this part and do some modifications so you can see where this really comes in and is a bit more useful. So I will hex mesh these solids, the material. So without the Hex Mesh, or sorry, the Mesh Control Explorer, the meshing toolbox didn't always work so well for hex meshing. It didn't really give you the same automatic, easy updates that it would for surface meshes. With the Mesh Control Explorer keeping those links between surfaces updated, it works quite a bit better. So we could go into mesh sizing, say we want to increase the number of elements here, we can click on that. And just like it does with surface meshes, it's going to delete, update, and remesh. And you can see that went from 50 to 51 elements, and that is propagated through all of these other solids. Go ahead and turn off our geometry. And you can see how that curve count propagates through. We can do this along these other edges as well. And we can even apply mesh approaches. So if we go to the mesh surface option, say I want to enforce a mapped mesh on this face here. So I can set that up, and then when I go back to mesh sizing, maybe I increase along this edge, that mapped meshing is going to propagate it through to here, and you can see it wrap around to the backside as well. So it's making updating your hex meshes a lot more easy, more dynamic, and you're not going quite through the whole same routine of deleting and remeshing and resizing. I used to be in the practice of creating groups of different curves. Maybe I want all these curves at 30 elements and all these circular curves on the edge at 50 elements, and I would set up groups so that I could number them. It worked well, but it was laborious. This new method here is really quite nice and makes things quite a bit easier. Now, that's just kind of one of the new meshing things. I'd say this feeds in well to some of the common meshing approaches for surface and hex meshing. It just makes it a bit easier and a bit more automated. But as the Siemens family grows and as they kind of acquire and expand their offerings, they have more technology available to them. And one of the new ones with 2022 is the automatic hex dominant meshing. This came from, I believe, Flow EFD, which is a CFD program. Once that was acquired by Siemens, the sharing between the meshing technologies is kind of between the different tools and is really quite useful. This is similar with Star CCM Plus, another great CFD code. A lot of their high-end meshing approaches have been adopted by Femap, and you can now use those for surface and solid meshes. So there's a lot of great technology sharing here. So I want to talk about these new sort of third-party meshing tools that have been integrated in a couple of different ways. We're going to see it with hex meshing. We're going to see it with tetrahedral, and then also with plate meshing, and see how we can use these new tools to affect all of those. So let's get back over to Femap. Now, before I get into the hex meshing, let's take a look at some geometry here. So I want some geometry that is not necessarily automatically hex meshable like this was. This was all carefully split into shapes that you could extrude or revolve, so it meshes just fine. But that's not always the case. In fact, that's rarely the case for any sort of geometry. So let's import some geometry. If you're ever looking for sample models to work with, if you go into the Siemens directory under examples, there's plenty of geometry and sample models to work with here. This assembly model is something that I've used for years as a classic hex meshing example. Now, it doesn't automatically hex mesh because some of these features extrude along the z-axis, some of them extrude along the y, and when we try to do that standard hex mesh, we get this red here showing that it's not gonna work. And it says so in the message window as well. We can slice this up and get the classic methods to work, but we can also now use the Hex Mesh Bodies tool. I'm gonna select this here. We can grab a material for it. And we get a little different dialog box than we're used to. And there's really a shift in the methodology or the approach to using these new meshing tools. You don't really want to mesh your part and then do everything else in terms of boundary conditions or connection regions, because it's not going to adhere strictly to the geometry. It's going to vary, it's going to drift from curves or points, and it's not going to be such a hard point there for all of those, because it's going to really try to work for an ideal mesh quality. And it's going to use a target mesh size, not a fixed mesh size, but a general target that you're working towards. So I think it's really just worth opening up some example models, playing around with it, comparing the two methods, and seeing how the two differ, because it really is a new approach. So let's just go with all the default settings here, and and see what it gives for us. There we go. So didn't take too long. We have a hex mesh part. We can take a look under the model info tree for our different element types and shapes. And you can see it's called the automatic hex dominant mesher because it's not all perfectly hex mesh. We have mostly bricks or hexahedrals here. If I turn off my geometry, you can see most of it is hex elements. We also have some wedges. That's always the case when you're trying to hex mesh. But the thing that makes this different is the fact that we end up with pyramids and tetrahedrals as well. So to get this to work automatically, there's just going to have to be a few transition region elements. And as long as you're not having a large concentration of pyramids or tetras in your regions of concern, or a transition element in your region of concern, it's really not too much of a big deal here. I've tried this on really complex geometry, and sometimes it works, sometimes it doesn't. It still is best with what you would consider classically hex meshable geometry. The more complicated and curvaceous and something that's generally lends itself well to a tet mesh, you're going to end up with much more of these transition elements, and you might not really have a whole lot of time savings or node count savings in using this tool. All right, we're going to come back to this in a bit and kind of talk about the proper workflow for it. But I also want to explore these new meshing tools with different element types. So let's take a look at used with tetrahedral meshes. One of the things that is becoming more and more prevalent, especially with the capabilities of additive manufacturing, is topology optimization. Now, this has always been to me, a really fascinating tool, way that you can apply a large variety of boundary conditions and optimization goals and have it generate really an ideal shape for you. It's fascinating. The problem with it is topology optimization really generates a lot of geometry that isn't manufacturable. You end up with these very organic shapes like this, and you can't easily machine something like this. However, with additive manufacturing, this stuff is becoming a lot more useful. Now, this is just geometry right here. If I turn off points and curves, it's a little bit easier to see, but this sort of tessellated STL triangular face geometry, this is not uncommon to be generated by a topology optimization tool. It's also something that's commonly used for additive manufacturing as an STL file with these triangular faces. Now, as you could imagine, classic meshing methods with Femap, this could be a bit of a nightmare because you have so many curves, so many points, so many surfaces that your mesh would have to follow all of these geometric entities, and you can end up with some real messy meshes here. The body mesher, these new meshing tools, don't really have to adhere to all of that, so it works differently. Let's just go ahead and use this. This is going to be under mesh bodies. And we're going to go with a tetrahedral mesh. I think for my target size, let's just go ahead and measure the model. How big is this thing here? That's about 0.3. Let's do 0.1 across here. And we'll leave everything else as a default. Give it a material and a property. Okay, so we'll let this churn. I went through this practice already to kind of see what would happen. And one of the things that I wanted to compare was the body mesher to the previous popular approach for TEP meshing, which is geometry preparation. Geometry preparation would identify, based on your target mesh size, all sorts of small entities, slivers, and small surfaces that you wanted to get rid of. So it's still a really useful tool, but I wanted to see how the two compared against each other. Now, while we let this guy churn over here, I'll show you some of the results. And working with the same geometry, the same mesh size, same version of Femap, everything, this is the difference between the two. The body mesher took about a minute, and it came up with a model using about 250,000 nodes. That same technique, sizing, meshing approach using geometry preparation took about 4 minutes or so and ended up with something with a lot more nodes, over 600,000. And that's because it has to follow the geometry much more strictly. You can see within these openings of sort of this clevis region here, geometry preparation didn't really mess with that. That left a lot of those fine triangular faces in there, where the body mesher overrides that and works towards a target mesh size rather than adhering to the geometry so strictly. So if you're worried about getting something meshed up quickly, reducing your node count, the body mesher could be the way to go. And it could also be faster as well. One other thing I noticed with this was the mesh quality. The body mesher gave me Jacobians between 0.6 and 0.8. There's actually only 13 elements in this upper range of poor element quality in this. As for the geometry preparation, you're looking at 500 elements in that same range. And you can see these little red sliver elements here scattered throughout wherever there was small, complex geometry. And it actually ended up with some poor element quality, even above 0.8, closer to 0.9. So it was definitely a win for those two, but it's important to realize that some of the limitations of this, since it doesn't strictly follow the geometry as much, depending on your mesh size or depending on how you set this up, you could be losing some of the small features, and you can lose associativity between the mesh and the geometry. So their recommendation for this tool is to start with boundary conditions, connection regions, everything that you would apply to the geometry in terms of analysis inputs. You want to do all of that first, because once you come through with the body mesher, it's going to recognize those as almost protected regions. It's not going to pave over important details if you're using those details for boundary conditions or connection regions. So what I had done as sort of a simple example is this assembly here is I went through and applied my boundary conditions first. And that way I know on these surfaces here, on these curves where I've applied these loads, that this tool, this body mesher, which is really hex mesh bodies or tet mesh bodies, same approach, isn't going to pave over those details. So let's do this again. This one will be a hex mesh bodies. I'm going to set 0.05 target. Now, if I'm going to be using hex mesh or dominantly hex mesh, I don't want to use mid-side nodes. And I'm going to use this all but bricks option. And that means it's only going to put mid-side nodes on the tetrahedral elements. All right, we'll let this go. Now, the problem with a combination of tetrahedral elements with mid-side nodes and hexahedral elements is that you have parabolic and linear elements playing together. I have the feature line option turned on. Let's turn off my geometry. So these dark outlines you're seeing is from this feature lines view option. And it's actually going to give you an outline between different element types. So I can turn that off. But let's take a look a bit closer at some of these transitions. So when I go to type, here's all of my linear elements, and here's my parabolic elements. And when we look at our nodes in those regions, you can see some of these triangular elements with mid-side nodes, some of the hexahedral elements without. And that's where some of the new post-processing comes in. Just the same way that Femap, the feature line tool, sees those as a discontinuity, different types of elements next to each other, your results would see that as well. So if we're going to analyze this part here, let's go ahead and set up a quick static simulation here. You could see breaks in your contours. You can see discontinuities in the colors of your stress results because Femap is recognizing different element types here. Let's go to the post-processing toolbox, and we'll just put some von Mises stress on this. And I'm going to turn off the feature line. And I'm also going to adjust the legend a bit to make this a bit easier to see. All right, so where I found this most noticeable was in some of these regions here. If we turn off things like our filled edges for our element, you can clearly see some sharp breaks in the mesh. Now, around here, we have a very smooth contour. It'd be hard to draw exactly where those element divisions are. But in this region here, it's a bit more obvious where we have these breaks. And those breaks are coming from the fact that we have parabolic and linear elements attached together. Femap recognizes those as the different types and doesn't automatically average stress results across those boundaries. So they have added in the option to not break the averaging scheme of your stress if it's a linear parabolic change. you can see as we turn this option on and off, you can get those discontinuities in the stress contour to go away. So this is a recommendation. If you have a mixed mesh like this, you would turn this off. Stress is continuous through a continuous part. We would not have a step change in stress like that. So I'm saying it's more realistic to turn this off for this particular application. And you can see once we have our filled edges on, as we transition through those different element types, our stress contour is nice and clean. Okay, so the last application of this new meshing technology, the body mesher, is with surfaces, and we haven't really looked into that yet. Let me clean up my view here a bit. And I have a model that we've been working on recently. It was something that identified that we maybe wanted a bit of a finer mesh. So in this region here, you can see some of the high stress along this, but it's a strong stress gradient across the single element. This is probably a scenario where we would want a finer mesh to really capture that stress gradient a bit more. And again, if you're an experienced Femap user, you know you can come in with the meshing toolbox, update your mesh sizing on curves, and it's going to automatically update the mesh as you go through and update these curves. But sometimes you just want a bit more of an aggressive approach. If everything is connected together here and we're not really trying to finesse a very specific mesh, we just want to do a quick and dirty what happens if this is a much finer mesh size. So let's start by measuring the existing mesh size. Measure here to here. All right, that's about 0.58. I'm going to isolate just this side panel here using the draw erase toolbar. Here it is. These floating lines here, again, that's the feature line option. You can have that to draw elements even if those elements are hidden from view. It can be nice for some context in the model. I'll go ahead and turn that off. But let's use the new body mesher to refine our mesh in this region without picking curves one at a time using the meshing toolbox. So we can do this with the mesh on mesh option. So this uses the existing elements to define the geometry or define the space that we're working with. And then it will then create a new mesh using that as its basis. So let's say we're just going to grab elements in this region here around where this was seeing some high stresses. I might want to get a clean line along here. That looks pretty good. Okay, so previously we were at 0.58. Let's go down to 0.25 for our target size. And rest will just stick with our default options here. It disappears just because I was using the draw erase toolbar, but if I switch over to hide some of these entities, there we go. You can see the new mesh size or the new mesh that it generates on there. It's really actually kind of a visually appealing mesh pattern, dominant quads. You'll notice on this inside connection too, where I had this rigid element, since this portion of the structure was defined by the existing mesh, it maintains those nodal locations, and I don't have to worry about rebuilding the rigid element that connects to that region there. So this is a great way to add mesh refinement to portions of your model very quickly and resulting in high quality elements as well. So it's really quite nice there. All right, let me jump back over to my presentation. There's so many new features here. I want to make sure that I didn't miss anything. Hex Mesh Refinement, okay, there's another great new tool. Sort of similar to the mesh on mesh. If you had an existing hex mesh and you really wanted to refine just in a specific region, you can use this mapped hex refine tool, just like I did with the mesh on mesh for the surfaces. This is also useful if you might have some sort of legacy model, something that doesn't have geometry associated with it. So maybe you don't have the option to use the meshing toolbox. This mapped hex mesh refine could let you update that mesh without using the meshing toolbox. All right, I believe I have a nice example for this as well. Now, as I've explored this tool, I have found some limitations to it. So let's say, for example, that we wanted to refine the mesh in this region here where there's clearly some sort of bolted connection or welded connection there. I'm going to darken up the feature or the filled edges just so you can see the mesh a bit better. All right, that should be a bit easier to see. Now let's do this mapped hex mesh refinement. Just like mesh on mesh, we select the elements we want to update. So this is under editing, mapped hex refine. Let's select this region here that we want to update. We can highlight to show where it's at. We can expand that region if we want, or kind of shrink that region. And we click OK. And it goes through, splits those up, and connects it in with its neighboring mesh. So we have a great way to refine the hex mesh. I said I've run into its limitations, and if you've gone to the seminars in the past, you know that I'm not going to pull punches here when the software doesn't work. So I explored this in other zones of this model. For example, there's some steps and some small blends in this section of the structure. I wanted to refine that as well. And I do mapped hex mesh refine and try it on something a bit more complicated like this. Must be a convex region of all hex or wedge elements. Well, I know I have all hex or wedge elements, but this region is not convex. I have some concave faces in here or some sort of topology that doesn't quite play well with this tool. So it's not a cure-all, but it does have some really great applications. All right, just browsing through. I think the last bit that we want to address in this new features update is post-processing. So we talked about the contour options. I also want to talk about JT files. And one other tool, we'll sneak this in before we run out of time, is the mesh interference check. So if you're working with models that have lots of different components that might be in contact with each other, this is a very useful tool. So going back to this truck body here, I have a lot of different components that I have mid-surfaced and meshed, and a lot of these I want to be in contact with each other. I want these different faces to contact. And if you've worked with models using contact before, you know you can run into trouble if there's gaps or there's interpenetration between the element faces. Sometimes that's just a modeling error. You want to ignore it. Sometimes you want to account for that. You want those interferences to act as a real interference or press fit. Sometimes you want those gaps to act like gaps and have to close up before they can carry load. It's always a bit hard until the analysis is actually done to know what your initial and deformed gap separation or contact separation gap was. But now there is a pre-processing tool under check mesh interference, that helps us find this here. We can create a group. I'm just going to go with my default settings, and it's going to check the model. It's going to build a group of all the elements that have interference, and then it'll also highlight here. So you can see some proximity where my floor is sitting on the subframe. Some of the internal structural elements of this cabinet interfere with the cladding on the surface. This is all different interferences that I would expect, but it's a great visual tool to check this out. One of the nice recommendations from the Femap team was the use of these tolerances, your interference factor and your proximity factor. So with the defaults, you can kind of see where mesh is adjacent, but you can use the interference factor to actually shrink the mesh, give it a bit of a gap, and that's a nice way to see if you only really want interferences. The proximity factor is a good way to artificially grow the mesh, and that way you can see where things are close but not overlapping. So it's not just an interference check, you have some options in the way you use this tool to see when things are close, when they're adjacent, or when they're interfering. And this can be a great tool to help you kind of choose what sort of contact options you might use. All right, I've got a bit of time left. The last thing I want to get into today is the JT files. And JT files, it's a common file format, and it's something that's been supported for quite a while by Femap, but they've added updates to it, which make it much nicer. So the broad overview of this is it's a 3D file. You can download the viewer for free, so you can share your analysis data with people, and they don't have to have Femap, or they don't have to use an instance of Femap. If you have a limited number of licenses, you don't have to use up one of those licenses just to look at some results. And they keep adding functionality to this. So you can just Google JT to go, you'll find that on the Siemens website and download that for free. As far as generating these files from Femap, let's jump back over to Femap here. I'll use my assembly here, and this is going to be under File. It's a bit odd. It's under Picture and Save JT. This is where you do a lot of your post-processing. If you want to save videos, animated GIFs, etc., you can use this picture option here. But we're going to do Save JT, and we can give this a name. This is also available under Teamcenter Visualization, as you can see. Here's all of the different options you have. You can choose to give the model some organizational granularity with properties, materials. You can choose to draw your beams as cylinders. So this is probably most useful if you have very consistent bolt sizing throughout an assembly. You can get them to draw as a cylinder rather than just a line. And you can work with multiple output sets now as well. And this is the JT to go interface. I believe it would look very similar to what you'd see in Teamcenter Visualization, but here's all the different options, similar to the Femap model info tree where you have the checkboxes and you can look at your different element types, your different components of the view like the legend, the color bar, etc. You can rotate, zoom. So I think this is a great way to be able to share information with really no cost. You can download, you can have clients download this, so if they want more than just a static image of the stress results, they can have something 3D to spin around, to look at. It can be really a great tool. All right, so that puts us near the end of our time. Let me see if we have questions. We had one question answered. We're done. Okay, so just another reminder, we've got plenty of other seminars on the website that I would encourage you. If there was anything today that we talked about that was a bit too fast or something that you haven't covered before, these are some of the recommendations, some of the newer ones. Model flow and organization is really useful for navigating the interface. Best practices is just kind of an introductory to Femap, how to get from geometry to post-processing. And then some of the more advanced stuff like working with presentation graphics, surface modeling, and plate meshing. Those are for some more of the experienced users or people that are looking to use some more updated methods. Thank you again for your time. Have a great day, and please reach out to us if you need anything else. Thank you very much.